Good evening to all of you. As we all know, class 12 course is running now as electrostatics. Today, I am going to take a special lecture on the time period of a simple pendulum. It is also applicable, or you may take advantage of this in class 12 course as well. So look at here. The time period of a simple pendulum here. The time period of a simple pendulum we divide for simplicity into two parts. One part is time period of a linear pendulum, and the second one is time period of a nonlinear pendulum. Nonlinear pendulum. So, in the two way, we have been categorized it, but these two way, one is called linear pendulum, other is called non-linear pendulum. Why it is called linear or non-linear, I will tell you today in this class, but both of them may be studied by mechanical means, by using the Newton's law of equation. Mechanical means mechanical way, in fact, and same things we will study under certain limitation by dimensional analysis. Dimensional analysis. So before going to discuss the time period of a simple pendulum by taking the linear or non-linear, by the way mechanical or dimensional analysis, we have to understand certain terms. So firstly, we are going to give you the concept of certain terms. So first of them is phase. What we mean about phase? To understand phase, as we all know, here the space is empty. What does it mean? Actually it is empty? No. Because at least oxygen is present there, that is why I am taking the lecture. However, proportion of oxygen is approximately 21, nitrogen 78, other gases as well present in the room. So to understand phase, firstly, we imagine here a level known as the reference level. So here is the reference level. Okay. So from this reference level, take another level here known as level of observation. So this level is at a height of h from the reference level, lower hand, here the left hand, is the reference level. Here the right hand, the upper, is known as the level of observation. Okay. So at the level of observation, what we observe? We observe, or we imagine to observe, because we have nothing to see here, where the oxygen, where the nitrogen, where the other CO2 or any other certain inert gases is there. So we imagine certain molecules of a gas is just going up. However, certain may be going down, maybe at certain angles. Anyway, but we are focusing on those which are just going up. So this situation, which is in space, so just we are going to take it into the board. Look at here. We will discuss the same thing on the board. Look at. So here is the reference level. Reference level. Now at height h, level of observation. Level of observation. Level of observation. As we said, certain particles is just going up, and we are focusing on that only. However, too many particles moving randomly in a very zigzag manner, or you may call it in very different manner, certain going down, certain angles, this way or that way. But we are focusing on those particles which are just going up. So that is why just we are indicating those particles like that. So the particles, we are focusing on that. All are at height h, and they all are going up. What does it mean? It means that they have same position and same velocity. Where? On the level of observation. From where? From the reference level. So now we call it, those particles are having of same position and same velocity, so they are in phase. Carrying phase. So that is why in this way we have got the concept of phase. So just I'm going to write for the sake of your convenience here. Those particles are having of same position and same velocity are known as in phase. So in this way we define phase. Okay. Now we are going to understand in the number 2 is the wavelength. What is wavelength? It is distance between two consecutive particles which are in phase. So two consecutive particles. Look at here. If you take this particle, position is h, is going up, and the next one. Consecutive means just next one. The next one is here. So this particle is again at height h and just going up. So now we call these two particles are in phase. However, Too many particles are in phase, but these two are consecutive, so distance between them is known as wavelength. So what is wavelength? It is distance between two consecutive particles which are in phase. So the two term we understand right now, phase and wavelength. Third one is the time period. Third one is the time period. So here time period time. So to understand time period, we think of to and fro motion or back and forth motion. What is this? To understand this, we may take a spring mass system, or we may think of a particle is in to and fro motion about a point. However, the point is also known as mean point or mean position. So we will discuss and we will see more when we take up the chapter simple harmonic motion. But right now here we focus on that. Here is the mean position. The particle is going this way, coming back, goes beyond, and then coming back. In this way, the motion is to and fro motion here, or back and forth motion. Okay. Now look at here. So it is already in the to and fro motion. However, there is a certain resistance is there, air resistance is there, maybe any dissipative force is there, but we assume they are negligibly small. Or this is the ideal case of to and fro motion. So let us see here. So it is continuing without any hiccup, without any resistance, without any disturbance. So the particle, say at t is equal to 0, we observe this is going right. Okay. So it arrived at say A, and then back there arrived at the same position. So usually this position say O. So particle we have been seen earlier crossing the position O, that's called the origin, and gone there at A and then come back and again arrived at A. So in usual sense, we mean that one thing is completed or one trip is completed in usual day-to-day life. But here in the concept of time period, it is still not a one thing completed. Why? Let us see. So if come back here, so its position is same, but its velocity is in the opposite directions. So it swings from here and goes at B, again come back from B because it's to and fro motion. So again arrive at the same position, but right now the velocity also becomes same. As we know, velocity is a vector physical quantity, so their magnitude and direction both are same. However, we are taking first time, maybe second time, third time, fourth time, fifth time, but for the time period, the first time when the position and the velocity become same, then we call it now one thing is completed. One happening is happened already. So the time required in completing one thing here, once the same position and same velocity, so this time elapsed is known as one time period. Okay, so here the little bit different from the one thing or one thing is completed rather than day-to-day life. So it is a slightly difference here in case of a phase. So in case of phase, we have been seen also that same position and same velocity. Here we not in the same exact manner, the same velocity, but we say here confidently that once its position and velocity become same, because the single particle here in to and fro motion. That is why I am telling like that. So the time period, this way we are going to define here it is time required. It is time required. It is time required to complete one thing. Exhaustive definition, mind you, one thing. What is this? It is called time period. What is time period? It is time required to complete one thing. One thing, maybe anything. Suppose the fan is moving like that, again comes to this position, one thing. However, we take one of the particle of the blade of the fan, so its position and velocity first time becomes same because one thing is completed. So just I am going in this way, I am coming in this way, just when it started here, same position, same velocity. So one thing has been completed, and the time required in completing the one thing is known as time period. Okay. So the time period is very important for us because time period, time period, it means not a time. So no one going to define time, or no one yet have been defined what is time. So just we call it time interval. Period, it equivalent to interval. So it is time period or time interval. Okay. So now here the last article regarding this simple pendulum is the frequency. Okay. So again the extensive definition, exhaustive definition of frequency is that it is number of things happen. Number of things happen in unit time. That's very extensive and exhaustive definition of frequency in a unit time. So generally we understand in 1 second how many things happen. So it is called frequency. No. It's all depends our convenience. So what is the unit time? It is already our perception about unit time. We may take 1 second, we may take 5 minutes, we may take 10 seconds, 29 days, 365 days, 24 hours. Are you getting me? 24 hours. The earth rotated one complete rotation in 24 hours. Earth orbit around the sun in 365 days. So that is why it is known as frequency. Unit time is 24 hours. Unit time is 365 days. Unit time is 29 days sun orbiting around the earth like that. You may take anything as per your convenience. So this is called frequency. So now we are in a position to understand the time period of a simple pendulum. So now just we are going to discuss here, but firstly by the mechanical way and also of linear pendulum. So what does it mean, linear pendulum? Look at here. Firstly, what is pendulum? So here is we take a massless string. What does it mean? It means very small mass, negligible small mass. And one end is already pegged here, pegged, we may call it fulcrum, about which it oscillates. Here is the bulb of mass small m, however not a very big mass. If we take a very big mass, then we have to take the center of mass as well, and we have to take the distance from center of mass to that of the peg. So we are not going to be complexity here. We take a very small mass, its center is very nearer to the end. So this is the length, this is the Okay. So this is the length of the pendulum L. So just we are going to understand the mechanical way. We'll take later on the dimensional analysis way to understand the time period of a center. But right now, mechanical way of linear pendulum. Mechanical way linear pendulum. Mechanical way linear pendulum. Linear pendulum. Linear. So basically linear pendulum. So in this case, as we know, so how it oscillates. Put it here and aside at certain angles and then let it go. And already we assume that there is no any air resistance is there, no any dissipative forces acting in the medium. So it continues to oscillate for forever. Okay. So here we aside it at certain angle theta naught and then let it go. So it sometimes comes here, come here in this position and then swings from here. So this is the path. Okay. So comes here and swing from here, then comes back, goes there, and in this way to and fro motion is already there, or the back and forth motion is there. So as we know, so it is the say supposed to be a center. L is the length which is supposed to be radius, and then so think of like that. It is goes in a circle like that because it is the motion is planar motion. So in this way. So this is the arc. This is the curve length. But our heading is that linear. It's the straight line. A straight line motion. So how one can say that arc become a straight line? No way. No way to consider. But this is the physics. We have to do certain things under certain assumption. So this theta now is very, very small. So we cannot assign 1 degree, 2 degree, 3 degree or 4 degree. It is not worthy to say like that. Because we have to take the linear pendulum, so theta 2 tends to 0 plus. Theta 2 tends to 0 plus. So in this way, suppose we join the say end point here. So this is the chord and this is the arc. The chord length will never equal to the arc length for a particular angle. Theta naught and theta naught say the 2 theta. But theta naught tends to 0. So this implies 2 theta naught also tends to 0. So this implies 2 theta naught also tends to 0. So this arc length is supposed to be a chord length. A chord length is a straight line. So now we call it the linear. And theta 2 tends to 0. However, we have been shown too many degrees there, 30 or 45 degrees looking. But to understand, but if we say here the theta, everything is happening like that, so it is not visible. So it is very hard to perceive it. So that is why we have been shown the two big angles here. So do not mean such a big angle is there. So in the limit ways theta tends to 0 plus. But to understand easily, so we take certain finite angles look like that. So in this way, so now we are going to a mechanical way to understand the time period of simple pendulum. Look. So now where this pendulum is oscillating, that's a very big question. So it may oscillate in any medium, whatever it may be, whatever is the artificial medium, whatever the natural medium as well. But the thing here, this pendulum is in the uniform gravitational field. We will discuss in the class 11th course. So no way it is the uniform by direction wise or magnitude wise. But here in this particular article, we have to assume like that. Okay. So suppose this is the earth, supposed to be a spherical. Here. So here is the peg. There is a pendulum we aside somewhere else. This is the radius of the earth, the mass of the earth, the mass of the pendulum m. So this angle is say theta. So this is the vertical. So now here mg is acting toward, because this pendulum is near the surface of the earth. So in general, if we do not make the sphere, it means we do not consider the earth, so we usually show the gravitational force is vertically downward. But here we have taken earth into account. However, when we take mg, then still there we have to consider the earth is there, some gravitational field. But right now earth influence is toward the center. However, in usual derivation, we do not show earth and the force is vertically down. But right now we are not doing like that. So here the force toward the center of the earth. Okay, this is here the mg. Now this angle supposed to be say theta and this is say phi. Okay, so now we draw the perpendicular like that here, like here. So this is theta, this is phi, proceed like that here. So this is theta plus phi, theta plus phi, theta plus phi. Now what are the forces acting on this pendulum? So that's the mg and the tension. Okay, so this is the mg toward the center. Tension is there. Now still we have two ways to take the equation of motion. Once directly using the net force by the Newton's second law, and now here we are using the torque equation. So take the torque about this mg force and the force of tension as well, because tension always acts away from the body. So this is the tension T. So the two forces visible here, mg and T. To take the torque of these two forces about the peg here, about the peg here. So what is this? To look at here. So the torque of the tension, because it's processed through the peg, the point about which we are going to take the torque. So the torque of this, the lever arm becomes 0, the torque of T will be 0. So torque of T will be 0 and the torque of mg here, look at here mg torque. So R cross mg. So here is the R vector, because we have taken the vectors from that positions, from where we are taking the torque. So this is the length L here. So magnitude of R, so this is the here L, magnitude of the force, we call it here mg, and the sine of the angle between them. So this vector and that vector, angle between them is this. So this is the sine theta plus phi. And this is the torque. This is the torque must be is equal to I peg. So this is the say point O. So IO alpha. IO. Okay. So but we look here minutely. If we assign it in this way, if we let it go, so it is not moving in the direction, you may call it in the sense here, one may call direction, but here in case of rotation we usually call it sense. So if we let it go from at the position at angle theta, so it not going in the sense it has been assigned. It moves opposite to that. So torque is restoring in nature. So we have to put the negative signs there. So we have to put here the negative sign. Okay. Why negative sign? Because torque is of restoring nature. That is why. So this implies alpha is equal to minus mgl over I out. Moment of inertia of that mass m about the peg, about the point of oscillation, and here sine theta plus phi. Theta plus phi. Now here we are considering what we are considering? We are considering linear pendulum. What does it mean? Earlier we said theta naught tends to 0. Here theta plus phi altogether tends to 0. So if it tends to 0, then there is merely the difference between sine of that angle and that angle. However, if we take the sine of that angle and the end of that angle, so that angle must be in radian measure, not in a degree measure. So these two are almost equal. So now we write sin theta plus phi as theta plus phi in radian measure. Mind you, in radian, not in degree measure. So minus mgl over I naught theta plus phi. Theta plus phi. These are the things here. Alpha is equal to theta plus. So now we have to put theta plus phi here. So this is the motion like that. In this way motion is taking place. However, for this phi, so this is the way like that, in that way. So this distance and this distance consider as a radius r. So it's very close to radius. So this distance is, however, looks very finite here, is very, very small. So we may write here minus mgl over I naught, and theta is, look at here, for the sake of writing what we are writing here. So here say angle theta, this is r and this is the arc length L. However, arc length or chord length here in this case, when theta plus phi tends to 0, this separately also tends to 0. How one can say theta plus phi tends to 0 and theta will be finite or phi will be finite? No way. No way. So theta plus phi, it means both are tending towards 0. So in that way, this is the chord length and this is the arc length are supposed to be equal. However, we have to write chord length. We understood arc length, then arc length, chord length, arc length. So theta is equal to L by R, supposed to be chord as well as the arc, because when theta tends to 0, both are almost equal. So here we write theta is equal to so here theta is, say this is the L, it's supposed to be radius, or here. So theta and phi, just we are going to convert one of them, either theta in terms of phi or phi in terms of theta. So because just about the peg the theta, so just we want to convert theta, theta remains and phi in terms of theta. Look at here, how? So I have told you that this length is supposed to be very, very small and that is also supposed to be very, very small. Not looking by this figure like this is the r and this is the radius 6400 kilometers. So this is the few meters like that. So that is why, because no way to show 6400 kilometer of sphere in this board, and you may think that. So this is the what we call unavailability of the space to draw such a big figure like that. So here from both the way, so we say that this distance, so this is and that is. So for this is earth, suppose this is the chord length, and for this pendulum is supposed to be chord length. So chord length belongs to both of them, for the earth and for this pendulum. So that is why this length must be equal. So this chord length, we know theta is equal to L by chord length by RP, that is called radius here. So theta is equal to L by, from that we write here theta into L is equal to phi into radius of the earth. So from here we write phi is equal to theta L by r. So put it here and get alpha is equal to minus mgl over I naught, and here theta plus, where phi is theta L by r. Theta L by r. Look at here. So this is minus mgl over I naught, and take theta common. So this is 1 plus L by r into theta. So this is supposed to be a point mass of the bob of the pendulum. So moment of inertia is mass times the perpendicular distance square. So this is the peg about which it oscillates. So this is the perpendicular length is L and the mass is m. So I naught is ml square. Write down here mgl over ml square 1 plus L by r into theta. So it is defined and not 0 as well, so it cancelled as well for theta. Put L inside, so comes out to be minus g 1 by L over 1 by r into theta. So in case of what we call, in case of angular pendulum, or in case of what is called, we call it linear pendulum. So this is the, because this value of theta plus phi naught is tends towards 0. So in that way, but here this is the angular acceleration. That is why I am telling you angular. So minus g like that. So this quantity turns out to be omega square, angular frequency square. So this implies right now here. So what g 1 over L over 1 by r is equal to omega square. So this implies omega is equal to positive square root of, because we the plus minus, so we have to take omega is positive, so we take the positive square root. So that is why it is g 1 over L by r. And we know the time period t is 2 pi over omega, so it comes out to be 2 pi over under root g 1 over L plus 1 r. So now we take case 1. Length of the pendulum is very less than radius of the earth. Then what we conclude? 1 by L over 1 by r is as good as 1 by L. So this implies time period is equal to 2 pi under root L by g. As we know from early school days, this result is simple. But under the condition, it is very less than r. Now we take case 2. Case 2 is what? Say L is equal to r. How big this pendulum is? Look at, there is 6400 kilometers. Where is the peg? Above the earth's surface, 6400 kilometers above. There is a peg. When we going to be set up a such a pendulum? So that's the science imagination. Okay? So now the time period becomes 2 pi under root. Look at here. This is now 2 by r by 2g. So it comes out to be r by 2g. Now the case 3. Case 3 is if L is very greater than r. So who one will going to set up such a peg and such a pendulum? Again, we imagine like that. So now 1 by L over 1 by r is as good as 1 by r. Then this implies time period is equal to 2 pi under root r by So in the mechanical way, they have been derived the time period. In fact, general formula is this one. However, very familiar and very acquainted formula, time period is equal to 2 pi under root L by G from early school days, resemble, and we got here also. But the general formula is this one, and we have a two case more what we have idea about the time periods. So case 2 and case 3. However, usually not asking, but you may encounter in the competitive examination, even in fact in the knowledge point of view it's very good. So this is the time period of a linear pendulum in a mechanical way. So next we will consider time period of a non-linear pendulum but under mechanical way, and then we will take the time period on the basis of dimensional analysis. Okay.